Hello to everybody. In this video, we will see how to estimate above ground biomass using airborne laser scanning data. These are the folders containing the files and data we will use during this video. For example, the Lidar files are stored in this folder. Firstly, we must generate the digital terrain model. To do that, we will use the software Fusion. The commands of Fusion must be written as MS-DOS commands. In the generation of the DTM, firstly, terrain points are filtered. To do this, the ground filter command is used with some parameters defining the terrain point filtering, and other parameters such as the output file, the resolution, and the input file are indicated. The input file consists of a text file that contains the path of each of the LiDAR files to be used. After filtering the terrain points, the grid surface create command is called to generate the DTM. In this command line, the output file some parameters regarding the resolution and the reference system and the input file are indicated. As the resulting digital terrain model is generated in the DTM format, we will need an extra step to convert a valid format that can be loaded in QGIS, such as ASCII. Apart from the digital terrain model, we also generate the digital surface model by calling the command canopy model and providing similar parameters to those from the grid surface create command. Then we convert the digital surface model to the ASCII format. This file must be saved using the BAT format. To launch this file, we can open the Windows command prompt. To change directory until reaching the directory where the batch file was saved. And then execute it by typing its name and clicking on the Enter key. Once the process is finished, we can visualize it on QGIS. Select the correct reference system. Next, we can compute the normalized digital surface model by opening the raster calculator and typing digital surface model minus digital terrain model. We select a name. We save it as GeoTIFF. We select the valid reference system and we launch it. As a result, we can observe the normalized digital surface model, where each pixel represents the height of the object with respect to the ground. The next step consists of visualizing part of the LiDAR data in Fusion. Therefore, we need to execute the Fusion software. To visualize LiDAR data in Fusion, it is required to load the background image of the area. In this case, we can load the normalized digital surface model. We load few LiDAR files. We also can visualize the plot saved in the shapefile format. To visualize the LiDAR data, we need to click anywhere on the selected area we want to visualize. Here we can observe the 3D point cloud. As we want to train and evaluate a model for the estimation of the above ground biomass according to some field data, the next step consists of clipping the Lidar data according to the plots. In this case, it's necessary to write one command line per plot. Here we are using the clip data command, indicating that the shape of the plot is circular, the DTM to normalize the Lidar data, the input file containing the path of each Lidar file, the output file, and the coordinates of the plots. These coordinates represent the lower left and upper right corners respectively. Therefore, if the shape of the clip is circular, these coordinates will represent the rectangle in which the circle is inscribed. After saving the file with the BAT format, it can be launched. Once the point cloud has been clipped according to the plots, it can be visualized in Fusion. To do this, we load the normalized digital surface model image, the clipped files, and we select the area to be visualized. Here we can observe the clipped point clouds according to the plot limits. Afterward, we will calculate the metrics for each plot. Firstly, it is required to create a text file indicating the path of all the last files containing the clip data. Then we can write a batch file using the command cloud metrics. And indicate the input and output files. This batch file can be launched and we can observe the CSV file where all the metrics are calculated at the plot level. It's important to keep the plot ID for each row. In this case, the plot ID corresponds to the input file name. Therefore, keeping this column will be enough and we can remove the column containing the path of the input files. On the one hand, there is a file containing the plot ID and the computed metrics from the Lidar data at the plot level, and on the other hand, there is a file containing the plot ID and the real values of above ground biomass measured at every plot. The next step consists of joining this information by the plot ID and without using any prefix. To do that, we can open both CSV files in QGIS and join them by the plot ID attribute. As a result, there is an attribute table containing all the information. This file must be exported as a CSV file. This information will be used to train and test the regression model for the estimation of the above ground mass. To do that, we open the Weka software. We load the data in the CSV format we have generated. The first attribute corresponding to the plot ID can be removed since it will not represent a dependency on the variable to estimate. As there are many independent variables, we will do an attribute selection. Here we select the wrapper subset eval as the attribute evaluator, the linear regression as the classifier, and the gradient stepwise as the search method. We select the dependent variable, which is the above ground biomass, and we launch the process. As a result, we can observe the metric selected. Weka shows its name and the ID they have in the Preprocess tab. Therefore, we can select them and also the dependent variable. We click on Invert and then on Remove. So that we keep the selected metrics and the dependent variable. Next, we can train and evaluate the model. In this case, we select the linear regression as the classifier. We will use one leave-out cross-validation. Therefore, as we have 84 plots, we write 84 faults and we launch it. As a result, we can observe the evaluation of the model through the correlation and other error metrics. Also, the equation for the estimation of the above ground biomass through the Lidar metrics is provided. This is the equation we will have to apply to estimate the above ground biomass in the whole study area.